Zootopia's ecosystem isn't impossible. It's one that uses these fictional monoliths of engineering and science, being the climate walls, and just couldn't possibly work in our real world, right? Well, contrary to what you may think, Zootopia is an entirely possible city that with just 8 fixes could be a functional utopia in all its insane glory, but if anything goes wrong, this place would become hell on earth. This video is an investigation on the genius of these climate walls and districts, where I figure out exactly how it could work and all the many problems that come with that. Let me explain. Now, to start this video, I want to lay out the biggest problems by each section or district, but first we need to cover the overall problems of energy costs, which I'll do now. Energy-wise, summertime will be way more expensive for keeping cool areas cool, like the tundra that needs 35 gigawatts to stay frozen, while heating the desert and rainforest would be around 23 gigawatts. Now, in wintertime, it swamps, but it also gets way crazier for keeping things warm, with 58 gigawatts needing for heating versus just 16 gigawatts to keep the tundra nice and chill. So across the entire city, Zootopia is moving around roughly 58 gigawatts of heat in the summer and a whole 74 in the winter. That is insane. It would require the power grid of a whole country to just run the city. But the important thing to note here is this is not electricity, it's heat. And because the city wouldn't be creating all this heat from scratch, it would be using giant heat bumps that would move heat from somewhere else into the districts. It would actually be very efficient. So when converting all that heat movement into real electricity use, the numbers drop by a lot. After heat pump efficiency, the climate system would actually only need about 12 gigawatts of electricity in summer and 19 gigawatts of electricity in winter. Still enormous, but no longer country level. But still, that amount of electricity is roughly the output of 7 to 8 nuclear reactors. Great. Okay, I'll make this nice and sweet. I'd love if you subscribed. It lets me do more videos like this, and especially like this, since this video has way more of an intense editing job because the added special graphics you're seeing. So showing love, whether it's commenting or subscribing with notifications on, tells me you want more of this. Either way, back to the video. So going forward into a specific district being Tundra Town, we did find a few issues in our plan of making this climate wall an overall district if possible. And really, at first, you would think it should be pretty easy. You just have to keep it cool, not anywhere near the task of keeping the other districts warm. This should be simple, said no one ever. Our basic goal is to keep an area of about 10,400 acres or 42 square kilometers cool 24/7 year-round. Now we need to have a base temperature without the climate wall and weather system, so we'll just use a Portland-like climate with a baseline of 39 Fahrenheit winter and a 68 Fahrenheit summer. We basically need to have Tundra Town always below freezing, even during the summer, to keep things working. Now the movie does show giant snow cannons, cold air vents, and the climate wall, which on the side blasts chilled air in to keep everything in a good temp. It's basically like a giant freezer. Now there is a reason keeping things cool is easier than heat, at least at first, mainly because cold air is way more cooperative. See, when you cool air, it becomes dense and naturally sinks, pulling in lower areas, and Tundra Town is built in a valley with the climate wall on one side and a mountain range on the other. This builds a basically giant bowl for the cold air to rest in, which means this district doesn't need to constantly fight rising heat the way Sahara Square will. But we still have many problems, being the heat leaking in from above, warm air blowing in from the sides, and most importantly, humidity. See, our first problem is actually cooling the air volume, and we have some real comparisons. Indoor ski resorts like say Sky Dubai have to keep the place cool and use 2 to 3 megawatts of continuous power to keep an area way smaller than Tundra Town cold. Now, throwing things up to Tundra Town to keep things cool, we'd use hundreds of megawatts of continuous cooling. That does seem kind of possible in terms of a mega project with a lot of investment, except there's a big difference between Tundra Town and a resort. It's outside. Now we have to deal with heat leaking from above. The air generates heat downwards from warm atmospheres above, and well, because we're in a bowl, the warm environment above us will leak air downwards. Thankfully, our climate wall is about 120 meters or 400 feet tall, which would make a massive column of cold air that can act as insulation against any heat. Still, even with that, we're adding another 35 megawatts to deal with heat loss, but that is nowhere near the real problem, being wind and humidity. See, wind is gonna be a big problem for our artificial environment, as it's not artificial. See, Tundra Town has about 5 miles of exposed border where outside air could very much blow in, and well, every second that's happening, we're gonna get wind pushing massive volumes of warm air from other areas into our district. Not good. Now, to deal with this problem, we're gonna add another 830 megawatts to keep things cool. That's almost a whole gigawatt. And we still haven't dealt with the real issue, humidity. All air contains water vapors, and well, when you cool humid air, moisture will condense into water, then freeze into ice. That process also requires a massive amount of energy because it removes the latent heat of condensation and freezing. It's why air conditioners drip water. Now I'm gonna ask you, imagine that for a whole city. Let's do some math. Worst case scenario, we get humid air entering Tundra Town each second in the summer, with 8.35 tons of water condensing per second, and in the winter just 3.2, with an added 3.1 tons freezing as well. Now the reason this all matters is because, again, counteracting all this humidity and making sure we don't raise the temperature with it or melt ice, we'd be using 21.1 gigawatts in the summer and 8.36 in the winter. To put that in perspective, one nuclear reactor produces 1 gigawatt. Tundra Town alone needs almost 30 year-round just to deal with moisture, not taking in mind the energy section I went over earlier or any other math we did in this section. Adding everything together, we would need 16 gigawatts in the winter and 35 in the summer. That is what a national power grid for a country like the US would need, being used for one single district of a single city. Oh my god. But all of this is ignoring a massive issue we can't solve. See, while we can counteract the moisture by just putting more energy and power in our climate wall to keep things cold, the removed moisture does have to go somewhere. You're literally pulling tons of water per second out of the atmosphere, meaning Tundra Town would constantly produce massive snowfall, huge ice buildup, drainage system problems, and literal daily blizzards. On theme, sure, but still not great. But we can actually fix all of this with a simple underground climate system as well as the wall. See, heating the outdoors with a wall is not very efficient, to be honest, from all the problems I've mentioned, and while at first I just raised the temperature down and ended up wasting so much energy, but instead we can just be smart about it. This applies to all districts, but especially Tundra Town. We just need a massive dehumidifier miles underground and specific systems in place to deal with snow and ice. Now, spoiling a little of the other areas, we can fix similar problems they'll face, like in Sahara Square, which is underground heating pipes to warm the sand, which means the ground to be hot instead of just relying on the wall. This is used in the real world in some countries to melt ice on paths and keep airports useful in winter. Now, in the rainforest, we just need hot water pools and steam vents on the ground, which would create a literal artificial water cycle. Our last fix we would use to help out the coldest district is gonna be the greenhouse dome solution. See, instead of fighting against the outside atmosphere, we just need to build a dome around the district to keep it separated. This fixes so much stuff because the whole reason we're dealing with wind and outside air is because Zootopia is built outside. And with that, I like to move forward into a hotter place, being Sahara Square. Let me explain. See, up to this point, it does kind of seem like the climate wall is, well, super possible, very energy expensive, but still possible. This all changes though when trying to make Sahara Square work, because oh my god, is this place a mess. See, cooling air outdoors is already difficult, but that is nowhere near the difficulty in heating outside air. The main issue here is that contrary to cold air, hot air when outdoors is not easily controlled, and the second you heat it, it will begin to rise. Now, why is this a problem? Well, the second we try to warm Sahara Square, the air is gonna flow upwards and just leave, and as it leaves, colder air will rush in and replace it. This is not good. We can actually use a real-world comparison for this, being outdoor patio heaters. Have you ever thought about how they keep outdoor seating at restaurants hot? Well, they use heaters that output over 40 million joules per hour. This does actually work in their situation by making a tiny bubble of warmth, but even that, anytime a gust of wind comes in, it quickly gets cold. So imagine that for Sahara Square, which is just a little bigger, and well, things would bleed. But if you remember in the last section, I proposed a solution being the greenhouse dome fix, where it just makes the tundra an indoor resort basically, and well, that is entirely possible for Sahara Square, would help a lot. This would fix the wind issue and also control the internal temperature way more, but it's not perfect, and we still need to get the internal heat of our chamber to be, well, very hot, which a dome sadly can't do all on its own. But I do have a few solutions. See, in the real world, there's a concept called the urban heat island effect, where cities trap heat due to concrete, asphalt, and glass that absorb sunlight. This makes large cities sometimes several degrees warmer than outside their borders. So, we want to make Sahara Square really hot, we just need to optimize it and get way more sunlight, but during this, we'd add another 3.5 gigawatts for heating as a bare minimum. Great. Now I do have a problem or more side effect. See, as the dome around the district is a single huge dome, then everything inside it, including multiple districts, would interact, and things good for one would not be good for others. For example, heating air decides humidity by a law. Air at 100% humidity heated by, say, 60 degrees Fahrenheit drops by 40 degrees. This is a good thing for sure when applying to our desert, until you realize the rainforest district, to keep it being a rainforest, would be pumping thousands of pounds of water vapor per second in the atmosphere, and if these districts are not fully divided, then Sahara Square is gonna suck all that wet air into it. And when you heat moist tropical air, it would condense into giant clouds right above our district. Now, thankfully, I think we just divide the ecosystems clearly, with their separate domes, or having the climate wall touch the dome and make a real wall, but it is important to note why that's very much needed. Now, the real issue after all of this is Sahara Square is gonna be a massive energy issue. With all the shit we are gonna give it to stay warm, making sure it doesn't ruin everything else, it'll be a planet-scale weather project, but also in that probably create massive consequences like deadly storms or tornadoes right outside the walls. Thankfully, we have a solution, being one that completely fixes our energy problem using a natural method: the ocean. See, the ocean is an absurdly powerful heat reservoir, and a small slice of ocean currents could supply over 332 gigawatts of heat at all times. And Zootopia is on the coast, meaning we just have water store the heat, and with ocean currents, new water we brought in, meaning the city just has to move heat, not generate it. Is this a perfect plan? Fuck no, but it makes it so we no longer have to be using 100 different nuclear reactors to heat things, and can instead use the natural heat right next door. And with that, I'll have to move on to the rainforest district, which is equally difficult in its own way, but I think I can make it work. Let me explain. The rainforest district seems pretty simple in the movie. It looked like a big jungle with rain and mist, and with our dome would just be a big zoo jungle. But even with that, scientifically, this place is a mess and would take a lot of infrastructure compared to the other districts, as it needs a very powerful literal weather system. Thankfully, the movie actually gives us a bunch of clues for this. We see sprinklers in the canopies, constantly making rain, with fog everywhere that we can assume is made by a huge industrial fog machine. An overall environment is by far the most lush and humid compared to our other districts. Now, to do this district needs to have a constant tropical condition of around 80 Fahrenheit and 80% humidity with constant simulated rainfall. Now, if you remember earlier, I proposed adding a bunch of warm water pools that could simulate a water cycle creating humidity, but that is not going to stop how much energy it takes to keep things warm. We're looking about 2.5 gigawatts in summer and a whole 10.5 in the winter. And again, that's ignoring humidity. To evaporate enough water to keep things so wet, we'd be using about 22.6 gigawatts in summer and a whole 43.9 in the winter. That means in the winter, this single district needs about 54 gigawatts just to stay warm and wet. For comparison, New York uses about 6 to 7, which means this one district needs the output of like 8 New York cities. And that's ignoring the rest of our hellish math. See, this setup has enough energy to create a thunderstorm every 6 days, and that would be inside the dome, meaning all the havoc contained with our animals. See, this is because the warm moist air that will be rising, then cooling, condensing, releasing heat, which creates updrafts, would then feed itself into a storm. And without our dome, this warm wet air would also be feeding into other areas and causing blizzards and constant rain. It'd also be incredibly difficult to do anything in this district, as rainforests are very destructive to any form of infrastructure, from metal corroding, wood rotting, concrete degrading, or mold. This place would constantly be battling against any effort at making it livable. Now, thankfully, we have a solution, at least to our energy problem. Remember earlier when I mentioned nuclear power wastes heat, and how all the energy we're using would end up dumping a bunch of heat waste into rivers, oceans, and just outside? Well, we can use that. That waste heat could easily be perfect for heating the rainforest, meaning we can very much calm down the amount of power it would take to make the rainforest so hot. This is basically just us using the extra heat from the cooling systems as free heat for the hot systems. Add in geothermal heat as a backup behind this, and the rainforest is actually super possible, as long as you ignore the horrifying storms inside it. And with that, we are done with our analysis of the climate walls, the districts, and Zootopia itself. And while horrifying and very dangerous, if you do a few fixes and use some science, we can make this place possible in all its horrifying glory. reality. If you would like more videos like this, click on this playlist right here for my overanalyzing science videos on nostalgic shows, or this video which YouTube thinks you'll like. Either way, bye!